Hello everyone, this is going to be a really quick supplementary video to the Lab 1. We're just going to go over the program status register a little bit more in detail here. So mentioned in the lab that the program status register, the top 4 bits, so bits 31, 30, 29, and 28 of the register are our NZ, C, and V flags. Those are the only ones we really care about in the program status register. So we're going to go over each one of those in detail here. So I've created just a little example program here. We're going to add some numbers and perform some operations. Remember that we're using the S variant of the various commands, so sub S, add S, and that will allow us to see the result in the program status register. If you do not include the S, you will not see the program status register change. So I'm going to pop into debug mode here, and we're just going to run through it. So we're going to start off with an example of the N flag being set. So that is this flag in our debugger right here. What we're going to do is we're going to load into R1 a hex 1 and load into R2 a hex 2, and we're going to perform a subtraction operation on that. So we're going to go 1 minus 2. Obviously, intuitively, we know that the answer is going to be -1. Now, on the processor here, it actually encodes negative numbers as 2's complement. So I don't know if you've learned 2's complement yet, but basically, it's not super important that you know exactly how it works. All that you need to know is that the 31st bit, the highest bit of the value, will determine if it's negative or positive. There's a little bit more to it than that, but for now, that's really all that you need to know. So we're going to load 1 into R1. We're going to load 2 into R2, so those are loaded in up here. And then we're going to perform that subtraction operation. We'll see that the result is all F's. Again, that's in 2's complement. That's how you represent a -1. But you can also see down here the negative flag was set. So again, all it's doing is it's checking that uppermost bit to see if the result is a 1 or a 0. And that's how it knows if it's negative. So for example, right, that uppermost bit there was an F. If we break that down into its individual bytes, it is a 1, 1, 1, 1. So that is the hex representation F into the binary representation right there. It is checking that bit right there. In this case, it's a 1. That's why we get the negative flag set there. Okay, moving on. We're going to do a example for the Z flag here. So that's the 0 flag. I'm going to load into R1 a 0, load into R2 a 0. If I add 0 plus 0, we know the answer is going to be 0. That's going to get stored in R0, right? So when we do this, we'll see that happen. It becomes a 0. And we can also see that the 0 flag is set. 0 flag will be set whenever your result is all zeros. It's probably the simplest flag that we're going to cover. The C flag is the carry or the unsigned overflow bit. It's both names, basically. Now, this will be set whenever the resulting operation overflows the register, right? We have 32 bits to work with. That is the maximum space that we have in our register. So the biggest number that we can put in that register is all F's. So what we're going to do is we're going to load into R1 a bunch of F's, and we're going to load into R2 a hex 3. Okay, so those are loaded in there. And let's do the math beforehand so I can sort of explain how this is going to work. So we're going to add together all F's into hex 3. So F plus 3, we're going to do this same as you would decimal math here, but it's in hexadecimal. So F plus 1 rolls that over to 0, right? So if we're adding a 3 to it, that means we'll have 2 left over, because 1 rolls it over to 0, 2 rolls it over to 1, 3 rolls it over to 2. And then we also have to carry 1, right? Same as we would regular math. 1 plus F, like I just said, is 0. And then we carry 1. 1 plus F is 0. Carry 1, so on, so on, so on, so on. And eventually we have 1 left that we're carrying right at the very end. But we've already filled up all the space in our register. So that carry bit there doesn't get put anywhere. But what it does do is it's going to set that carry flag. So if we step forward here, we'll see that the result should be a hex 2, and we'll see that the carry flag is set because we've overflowed that register. Just like that, we can see carry flag is set, hex 2. So hopefully that sort of explains the carry flag a bit better for you. The V flag is the signed carry bit. So again, when we're dealing in registers here, there's no concept of signed or unsigned numbers. But if we were to if we were to program in such a way that we were treating certain registers as signed, this is where the V flag would become important. So, like I said, the uppermost bit determines if a number is negative or positive if you're dealing in signed numbers. So in this case here, we're loading in a hex 7000 with the remaining zeros as well, and a hex 2000 with the remaining zeros into R2. So if we look at this this first number that we're loading in here, and let's pop back in here. So that was 0x7000000. So we're loading that number in there. So in binary, this 7 here is going to look like 0, 1, 1, 1, right? So that uppermost bit is currently a 0. It's not set. The number is positive. And we're adding to it 0x2000000. So let's add those numbers together here. Obviously, we're going to end up with a bunch of zeros over here. And then 7 plus 2 is a 9. Right, so that 9 now is going to look like in binary 1001. Right, so now that uppermost bit is set. The number is now negative in 2's complement. So if we were treating those numbers as signed to begin with, we have effectively overflowed our signed integer or signed number of some sort, right? So that is what will set the V flag here. So again, we're going to load in the hex 7000, the hex 2000, and we're going to perform an add operation on those, and we'll see that the result here should be a hex 9000, and we will see that the V flag will be set. If it works. I'm just going to reset it here, and we're going to step through it one more time. For some reason, the debugger doesn't like to execute the last instruction all the time. I'm just going to add an extra instruction after this, just so it'll hopefully work. Okay, and we'll step through that again. Okay, and add. There we go. So we get our hex 9000 here. You get the V flag set, and of course the result is now negative in 2's complement because we ended up with a 1 in that very first bit. So the N flag is also set in this example. So hopefully that explains a little bit better how the program status register works and when the various numbers or bits get set. And hopefully that helps you out with your lab assignment and the interview in the next lab.